Welcome to The Explainer. Today, we're diving into a pretty wild idea, a single mathematical language that could describe synchronized change everywhere, whether it's happening inside a tiny atom or across an entire galaxy. I know, it sounds a little bit like science fiction, right? But just think about it for a second. What if the fundamental rules that govern how massive galaxies move together could be described by the exact same math as how atoms behave? That's the huge question at the heart of this concept of co-movement. Okay, so here's our game plan to wrap our heads around this. First, we'll dig into the core idea, this theory of unified change. Then we'll pop the hood and look at the foundational toolkit it uses. After that, we'll see how it's actually tested in the real world. And finally, we'll explore the really big implications, its stability and these universal rules. All right, first things first, what is the big idea here? Well, this whole theory is about creating a standardized way to identify any system that's changing in a structured, unified way. Basically, systems where all the parts are moving together. And this concept has a name, co-movement. So at its heart, the entire point is to build a kind of mathematical filter. You can picture it like this. You pour all this messy, chaotic, noisy data from a system into one side, and what comes out the other is only the pure coordinated transformation. It's all about separating the real signal from the random noise. Okay, a mathematical filter sounds cool, but how does it actually work? To get that, we need to open up the UPT's foundational toolkit and look at the core concepts that make it all possible. The main tool, the star of the show, is something called the cutting operator. And I love this analogy. Think of it like a bouncer at a super exclusive club. It stands at the door, looks at every single motion happening in a system, and if that motion isn't part of the synchronized, coherent dance, it gets thrown out. Simple as that. So what happens to the motions that do get past the bouncer? Well, they get to join this very special group called the kernel. And you can absolutely think of it as the co-movement club. If a system's motion makes it into this club, that's the very first sign that we are looking at true unified change. Now, to officially verify co-movement, the theory gives us a super clear four-step checklist. First, you check the system's boundaries to make sure its edges are stable. Second, you run that motion test to see if it actually gets into the co-movement club. Third, you have to confirm the change is happening along a smooth, continuous path. And finally, you make sure that path represents a valid, legitimate transformation for that system. It's a pretty tough process to get through. So with those tools and that process in hand, we get to the absolute heart of the theory. It's all summed up in this one elegant theorem that acts as the final, definitive litmus test for co-movement. And this, right here, is the key takeaway. What this theorem proves is that these two things are basically two sides of the same coin. They are always true at the same time. If you can physically see a system co-moving in the real world, you can be 100% certain that the math will check out. Its motion is in the co-movement club, and its random energy has been totally filtered out. It creates this perfect, unbreakable link between what we observe and the math behind it. Okay, so what happens when a system actually passes the test? Well, this is where it gets really powerful. Because once a system is confirmed to be co-moving, the theory unlocks some incredible consequences about how it behaves. And the first big consequence is just how stable these systems are. Co-moving systems are incredibly robust. They don't just fall apart. Their synchronized state is remarkably resilient to outside interference. But just how resilient are we talking? Well, the math gives us a very specific guarantee. You see this formula? It tells us that even when you introduce a little bit of noise or error, that's the epsilon symbol there, the system's synchronized state, its phase, stays almost 100% stable. It just holds itself together. So in the end, this whole framework gives us four really powerful guarantees. It proves that a co-moving system's boundaries are locked down to protect it, that its fundamental rules are stable, and that its synchronized rhythm is coherent even with noise. But honestly, the biggest implication here is that last one. It creates a universal standard. It gives us a way to compare synchronized change in completely different fields of science, using the exact same language. And this quote from the paper really says it all perfectly. The definition of co-moving depends on whether its motion gets into that special club, the kernel, and follows a valid path. And the crucial part is, this definition doesn't depend on the specific scientific field, because these concepts are intrinsic to the theory itself. That's why it can be applied to anything from biology to cosmology. So what's the big takeaway here? What should you remember from all this? It's the creation of a common language. For maybe the first time ever, researchers in completely different fields could have a standardized, reliable way to talk about and actually verify this synchronized phenomena they're all observing. And that leaves us with a final, and honestly, a really tantalizing question. Now that we might have a universal ruler to measure this kind of change, what hidden connections between things like biology, physics, and even economics are we about to uncover? What new conversations can we even begin to have?